Now we're going to get into DeMoivre's theorem. DeMoivre's theorem allows us to raise complex numbers to powers. So if we have a polar number like this, and we want to raise it to a power where n is a positive integer, we can. Okay? And look at what you have to do. You have to raise r to that power, which kind of makes sense, but then you're going to multiply n, or whatever that power is, times theta. But you have to have a polar number. So in example 6, they give us a polar number and they want us to raise it to the fourth power. Here comes those exact values again. Right, so z to the fourth power would be the square root of 2 to the fourth power times the cis of 5 pi over 16, multiplied times 4. Okay, I'm multiplying 4 times theta. Okay, so the square root of 2 to the fourth power, that's the square root of 2, square root of 2, square root of 2, square root of 2. So that's 2 times 2, that's 4. And then I can reduce, and that's 5 pi over 4. I can ask for exact values because 5 pi over 4 is something I should have memorized in trig. If you need to convert 2 degrees, 5 pi over 4 is the same as 225 degrees. So I'm in quadrant 3. So that means cosine and sine are both negative. So I'd have 4 times the cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. So what's the cosine of 5 pi over 4, or the cosine of 225 degrees? It's negative square root of 2 over 2, and the sine is exactly the same thing. So distributing the 4, reducing, I'm going to get negative 2 square root of 2 minus 2 square root of 2 I. So I've written my answers in exact values and in rectangular form. I've used this theorem to take a polar number and raise it to the fourth power. Now I want to raise this number to the sixth power. Leave my answer in rectangular form. Well, this is in rectangular form. DeMoivre says you have to have a polar number. So one option is to actually multiply this out 6 times, means, and so on. 3 more of those. That's a lot of foiling. I do not want to do that. I want to use DeMoivre's theorem, and that's the beauty of it, so you don't have to multiply all those out. But you do have to have a polar number. So I need to change this to a polar number. So that means I need r and I need theta. Okay, so r is going to be the modulus, or the magnitude of z. So that's the square root of 3 squared. Remember, we just take the coefficient plus negative 1 squared. So r is just 2. Right, now I need theta. Alright, so the tangent of theta is the imaginary part over the real part. Again, that should be familiar to you, something you should have learned in a trig class. So when is the tangent equal to the negative square root of 3 over 3? You could use a calculator and it's going to tell you negative 30 degrees, or we can use 330 degrees, whatever one you feel comfortable with. But you should know the calculator would have even given you that. If you were in degree mode, it would have given you an exact value. So now we want to find this raised to the 6th power. So I want z to the 6th power. So I want r to the 6th power, and I want cosine I sine, and I want 6 times my angle. I'm going to go ahead and use that negative 30. So 2 to the 6th, I believe, is 64. 6 times negative 30 is 180 degrees. And yes, I need negative 180 degrees. So what is the cosine of negative 180? Yes, it's the same as the cosine of positive 180, which is 1. Nope. Negative 1, sorry. And the sign of negative 180 is 0. So believe it or not, this raised to the 6th power is just negative 64. Much easier than having to FOIL all of that out and collect like terms. It would have just been a mess. So using DeMoivre's theorem to raise things to powers is pretty easy. But if we can raise something to powers, we can also find roots, because roots can be expressed as powers. If we're asked to find so many roots, if you want to find the cube root of a number, there are 3 complex roots. The 4th roots, there should be 4 complex roots, and so on. So if you looked in a textbook and said, how do you find the complex roots of a complex number, you're going to be given this pretty scary formula. Not to worry, we're going to do it step by step. But we are dealing with polar numbers, right? So all polar. So example 8, I want to find the 4 fourth roots of the square root of 3 minus I. If you look back at example number 7, we had r and theta for that number. We had z equals the square root of 3 minus I, and we found its modulus to be 2. Again, refer back to example 7 for those numbers. And we also got theta to be negative 30 degrees or positive 330. So if I want to find the 4 fourth roots, what do I have to do? Right, so we have our r and theta, and now I want to find the 4 fourth roots. I know this is a scary formula, but we're going to take it step at a time. So our first root, because remember there's 4 of them, is going to be the 4th root of r, which is 2, times the cis of theta, and I'm going to use our 330 degrees, divided by n. N is what our root is, okay, plus, now since I'm in degrees, I don't want to use 2 pi, I want to use 360 degrees, again divided by 4 times k. Now what is k for the first one? It's 0. Right, so that's going to be 0, and that's going to go away. But before I make it go away, I want you to look at this. 360 degrees is equal to 90. That just means if you think about a circle, and we want a circle divided into 4 even parts, it would going to be every 90 degrees, much like the rose petal curves in the polar graphing. But it's not going to start at 0, 90. This is going to be our starting point. All right, so we're going to have our starting point and then 90 after all that. So our first 4th root is going to be the cis. 330 divided by 4 is 82.5 degrees, and then plus 0. The second one is going to be 82.5 plus 90, because again we want it evenly spaced around the circle. Our third one is going to be 82.5 plus 180, because that's another 90. And our fourth one is going to be, of course, plus 270, because that's another 90. Now if I added 90 again, I would get back to where I started out. So I want 4 of them. So I have 1, 2, 3, 4. Leave answers in polar form. So really the only thing I need to do is do some addition. So 90 plus 82.5 82.5 plus 180, that's going to be 262.5 degrees. And then our last one, add 90 again. I said add 90 again to this previous answer, or of course 82.5 plus 270 would be 352.5. Hopefully my addition is correct. So those are our 4 fourth roots of this complex number in polar form. let's do one more. Okay, so we want the 5 fifth roots of negative I. And again, we can leave our answers in polar form. So first of all, I need to know that z is 0 minus 1I. So I need my r and theta because I've got to use polar in order to use this theorem. So r is the square root of 0 squared, negative 1 squared, 1. Now hopefully you really didn't need to go through that. If you just plot that point, that is negative 1I. Right? And so the radius or the distance between the origin and that point is 1. And speaking of which, can we just look at that and know what theta is? What is it all the way around to here? Yes, 270 degrees. And that's the easiest way to do it when it's on one of the axes, is just plot it and say, what is this angle? So I have my r and I have theta. I need to know the fifth roots. So I need the fifth root of 1, which is going to be 1. Cosine I sine, your angle divided by the how many roots, plus 360, again I'm going to use degrees, divided by 5 times that k. So that's our spacing. This is our beginning point. So I have 1 cis 270 divided by 5 is 54 degrees. And then what is our spacing? Well, 360 divided by 5 is 72. But we're going to have 72 degrees times 0 as our first one. So we're going to have 1 cis of 54 degrees. What's our next one going to be? 54 plus 72. 54 plus another 72. So that's going to be 144. 54 plus another 72. Plus another 72. So again, here's our first one. Our second one's going to be, and you don't have to write the 1, it's going to be cis of, what is that, 126 degrees? Cis of 270 degrees. And then our last one, I believe, is 342 degrees. Hopefully I'm doing my math correctly. And so we have 1, 2, 3, 4, 5 fifth roots of negative I. I know this seems confusing, but kind of going back to our polar graphs, those rose curves, again, we would have, this is telling us our starting point, this is our spacing of all of those roots around the circle.